So let's start by looking at weight and normal force. So if we have a box here sitting on a surface, gravity is going to be acting down on this object. Remember, force is equal to mass times acceleration, so the force of gravity is equal to mass times the acceleration of gravity, g. This quantity here, mg, is what we call the weight of an object. When you measure your weight on a scale, you're measuring the force of gravity acting on you. Mass, on the other hand, remember, is like an object's resistance to a force. So your mass, your inertial mass, is different than weight. So do not get those two terms confused. Mass and weight are two different things. Mass is an inertial term, how you react to a force. Weight is the force itself on your body. So those are two different things. Now, if we remember just thinking about an object sitting on a surface, if that object is just sitting on the surface, it's not moving anywhere in this y direction. So that means that acceleration is equal to 0 in that y direction. So there must be some sort of supporting force on this box. That supporting force, that it would be equal to an opposite of gravity in this case, is called the normal force, or Fn. I like to use the notation F with the subscript capital N. Your book just writes a capital N there, but I don't want you to get confused with newtons, so I write F underscore N, or F with a subscript N on it. In this case, because there is no motion in the y direction, my Fn would be equal to the weight of my object, or mg, since those two forces would act to cancel each other out. Where it gets a little trickier is if we're on an incline. So let's erase what we had and look at how it would act on an incline. So if we have an incline, and let's say that it's at an angle of 20 degrees. Okay, so we have a 20-degree incline, and we have an object that's on that incline. And we want to know what would be the normal force acting on that object. So let's draw the free body diagram for it and see if we can figure that out. So there's our object. Gravity is going to be acting straight down, just like it always is. So there's gravity. We would have our normal force then acting perpendicular surface. That word normal actually means perpendicular surface. So my supporting force comes out 90 degrees from the surface and looks something like that. So in order to calculate that normal force, you have to figure out, well, how much of that object's weight is being supported by that surface? Well, it's not all of it because we're at an angle, right? Gravity's straight down and my surface is this way. So it's only supporting part of that weight, the part of that weight that is perpendicular to the surface itself. So to do this, we have to find vectors. And so what we're going to do is we're actually going to sort of tilt our axes so that our y-axis is perpendicular surface and our x-axis is parallel to it. So when we split up our force of gravity, it might look something like this. And then we have a 90-degree angle there, so we have our nice right triangle. And we would say this is force of gravity in the y direction, and that this is force of gravity in the x direction. And I'm not going to go into the geometry of it, but know that this angle in the triangle is equal to the angle on our incline. So that would be a 20-degree angle. So our force of gravity in the y direction would be our normal force of gravity, our weight, mg, times the cosine of our angle. And our force of gravity in the x direction would be the mg times the sine of the angle. And so this is a very, very important operation to be able to do. You're going to have to be able to do it to solve problems with anything on a ramp. But the nice thing is it doesn't really change. The only thing that changes might be the actual number you put in for your angle or mass, whatever. But the process here is all the same for all of those type of problems. And so, since our normal force, since there's no motion here like this as it's moving down the ramp, that would mean that FGY and Fn are equal to each other. So Fn in this case would be equal to mg cosine theta. And that's really always going to be the case when we're working these ramp problems, when we have something sliding or even possibly in the future rolling down a ramp. Tension is the force that acts on or within a rope or something where we're suspending an object. Generally ropes, we usually consider ropes to be massless because it makes things nice and easy for us. So for example, if we have a rope and we have an object here, maybe a 20-kilogram object hanging from that rope. Okay, we have our force of gravity acting down on the rope, and we have our force of tension in the rope that is holding it up. In this case, our force of gravity, right, would be our 20 kilograms, our mass, times the acceleration of gravity, 9.8 meters per second squared. And our force of tension, because this object isn't moving up and down at all, there's no motion this way, it's not bouncing or anything crazy like that or sliding or whatever. Our force of tension in the rope is going to be equal to our force of gravity. So tension is just, kind of that force, whatever force being transferred through that rope to whatever it is that's actually securing that rope and holding it. So tension, when we talk about a tension force, we're just talking about tension in a rope. So with forces, we just want to take a second and look at what we consider the 4 fundamental forces within the universe. These are forces that exist just because the universe is put together the way it is. Because the universe exists, these 4 forces exist. So these 4 forces, I pulled these right out of your book, are the gravitational force, the electromagnetic force, the weak nuclear force, and the strong nuclear force. These are in order from weakest force to strongest force. Which might be kind of surprising because we usually we think of gravity in our lives as being a fairly strong force, something that we have to deal with a lot. But it's actually the weakest of these 4. The difference is that we have the most experience with this. It's the most obvious, most easy to see. And because the Earth is such a large mass, it has a lot of gravity. And so we notice the effects of it relatively well. However, it is definitely, right, approximate relative strength 10 to the negative 38. That means it's 38 times weaker than our strongest force, our strong nuclear force. The electromagnetic force about 100 times weaker. The weak nuclear force 10 to the negative 13. So if we were putting these in order from weakest to strongest, these 2 would actually be reversed. Gravity and electromagnetic have an infinite range, but the weak and strong nuclear force really are only acting inside atoms, or even in the case of the weak nuclear force, within particles within atoms. So they have a very small range in terms of where they act. Gravity is only an attractive force, but the rest of them can be either attractive or repulsive, meaning they can pull things together or push things apart. The way these forces act are through carrier particles. These carrier particles sort of get exchanged back and forth between the 2 objects that are interacting, and that causes what we see in terms of the effects. Graviton for gravity, photon, which is basically just light for our electromagnetic force, the 2 W and Z, what we call bosons for the weak nuclear force, and gluons for the strong nuclear force. Gravity we see interact a lot. Electromagnetic, think maybe magnets, electricity for that one. Weak nuclear, you're talking about forces that are holding particles together within atoms. So for example, a proton is made up of 3 different types of quarks, and the weak nuclear force is holding those quarks together. Gluons and the strong nuclear force are acting inside the nucleus of an atom and kind of holding together the nucleus of an atom. And you can kind of see the strength of this if you think about, maybe a nuclear bomb. We're separating those things and we're sort of releasing this energy that's stored there all of a sudden. And you can see that, even for a small bit of stuff, we get a really big amount of energy for it. And so that might, be a good comparison for you when we're talking about how strong this strong nuclear force is. So those are the 4 fundamental forces, ones that you just kind of need to remember.